So can we start, Sam?
Sure.
All right. So today we're glad to have Sam Mundy from Columbia University, and the title of his talk is Eisenstein series, p-adic deformations, Galois orientations, and the group G2. All right, you can start.
Cool. Thanks, Jingwei. And thanks to Jingwei and the organizers for inviting me. This is exciting because I'm actually going to be with you guys next fall. So sort of a small introduction of me into the group, I guess. Yeah. So let me get started. Yeah. So my talk is going to be about a result on GL2, but to get that result, we need to go to a higher rank group, and that higher rank group is G2, and I'll describe this in some detail. The one disclaimer I should give is that Galois representations are going to be the main focus out of these three objects. I'm going to give half the talk on an overview of what the whole picture is, and then half the talk will be on the Galois side of it. So let's get started. The main theorem is starts with the following setup. So I'm going to fix a prime number p, and so any prime actually, and then I'm going to fix also a modular form. So Cuspidal eigenform, which is holomorphic. I'm going to assume that its weight is at least 4, and its level is n, and for simplicity, I'll assume p is co-prime to n. And I'll assume that it has trivial Nevin typus. So, for instance, the automorphic representation associated with it will have trivial central character in that case. Okay, so the theorem is going to be about f in the end, or about the p-adic Galois representation attached to f. And so to set that up, we get from this data, we get a unitary cuspidal automorphic representation of GL2, which is what I'm going to call pi sub f, and also rho sub f, which is a Galois representation attached to f by Deligne. So there's, I guess we'll get to it when we get there, but there's a little bit of an annoying normalization issue here. So this rho f is like the usual rho f, the one whose L series is the L series of f, and not of pi f, because pi f is sort of shifted. The L function of pi is shifted a little bit because I assume pi f to be unitary. But in any case, that's why you'll see like a bunch of weird numbers appearing in the talk. Okay. So here's the main theorem already, but it's sort of a vague version of the main theorem. You have to state some of these things precisely, but let me just give it. So I'm going to assume that the level of f by the end of the talk, the level of f will be 1, and I'll also assume that f is not a CM form. We need this for some big image assumptions for the Galois representation, but we'll get to that. Then, under the following two conjectures, so I need Arthur's conjectures, and I need a version of the global Langlands correspondence for G2, for cohomological representations of G2 for this to work. Under these two conjectures, we have that the Bloch-Kato-Selmer group, the Selmer group, so this is the symmetric cube of the Galois representation attached to f. And you take the dual and you twist by not 1 because of the normalization issues I was mentioning before, but by this number, where k again is the weight. And you take the Bloch-Kato-Selmer group of that Galois representation. Then this is non-trivial. This group is always non-trivial under these assumptions. Okay. By the way, if I'm going too fast, feel free to slow me down. I almost never give Beamer talks, so this is a little unusual for me, but yeah, please slow me down if need be, or ask questions or anything.
Are you proving that this automorphic form occurs in G2 in some non-tempered fashion in cohomology? What's the...
Yes, well, we will get to that. It will appear, so the G2 appears, the G2 starts to appear once you parabolically induce this up to G2, and then the L function, you'll see it in the Langlands, you'll see the symmetric cube in the Langlands method after that.
Right. So I'm trying to understand what, before you start with the Galois representation, if we're just talking about the discrete part of the spectrum, say, that Arthur will tell us something about, but not normally under G2.
Oh, yeah. Yeah. So
you're saying Arthur conjectures for who?
For G2. Sorry. Yeah.
Well, which Arthur conjectures? Not about the discrete spectrum, but about unipotent. What's his conjecture?
About the discrete spectrum? That's right. Yeah. Arthur's multiplicity formula. So
I thought he only did classical groups. So I'm confused. Okay.
Right.
So I guess they know those aren't conjectures. I guess the other ones are theorems.
Exactly. Yeah. That's
okay.
right.
I'm trying to catch
that's why
up
I'm
with
assuming them. Yeah.
But his conjectures for G2, he writes down the explicit discrete spectrum there conjecturally. I actually never saw that. All right.
We'll have enough information to know what part of the discrete spectrum we need to look at. But actually, I won't get into that too much in this talk. But yeah, I guess I can refer you to some work afterwards or something.
So was this previously known for any particular F, like for delta?
For any, what was previously done is if you remove the sim cube. This is Skinner and Urbon's work for Bloch-Otto for modular forms. And there's other work for other Galois representations as well. But the sim cube has not been previously done for any F. Yeah. And yeah, delta won't work because it's a CM form. So yeah, but
can you just repeat them? My memory is not so good on this. So and now Arthur writes a discrete spectrum for classical group explicitly. For exceptional groups, what does he write down?
So Arthur, as far as I know, hasn't written anything down. Maybe he has, I'm not sure. But the description that I need is in a paper of Gann and Gurevich.
Ah, okay. It's not okay. So okay, right.
Yeah.
Now I understand much better. Okay.
Okay. Great. Okay. So if there are no more questions, let me get on to the remarks about this theorem. So some remarks. So one thing I want to note is that when n is 1, so when the level is 1, we always have that the sign of the functional equation is -1 for this symmetric cube functional equation for pi f. And it's, yeah, so the central value is always -1. And in particular, the L function will always vanish. So Bloch-Otto is going to predict that this thing is non-trivial. And more precisely, actually, what Bloch-Otto predicts is this, that the order of vanishing of this L function at the central value, which in this case is s equals 1/2, is exactly the dimension of this particular Solar group. So this is, yeah, again, this is the twist that you need to put in to get the normalizations correct. But yeah, this is what Bloch-Otto is telling you in this particular case of the symmetric cube. Okay, so there are, before I actually get to the 3 main steps, let me talk a little bit about G2 because it's so important that we'll need to have a little bit in our setup. So the way I think about G2 in general is just as a, sort of via its root system. You can actually see a lot from its root system. Hopefully we can see a little bit of that in this talk, but so I'm just going to define G2 to be the split algebraic group over Q with the following Dickin diagram. So I write alpha for the long root. It's 3 times as long, or I guess square root of 3 times as long if you want, as the short root beta. So I think this is actually backwards from what some authors do, but I like, since alpha is the more important root for me, I'm going to call the long root alpha the short root beta. Here's the root lattice. I shaded the dominant chamber. If anybody cares about the root lattice, it's right here. This particular root will be a little bit important for us. In particular, multiples of this weight will show up. But in any case, I'm going to let P be the long root parabolic. So the levy M of P is going to contain this root alpha, or the root subgroup corresponding to alpha. And I'm going to, and also minus alpha because it's a levy. And P check, I'm going to write for the short root parabolic for reasons that would come clear in a second. So M check will contain beta. M check is the levy of P check. And then we have that both M check and M are both, they're both GL2s. So there we have two ways to embed GL2 inside of G2 as a Levy subgroup of a maximal parabolic. So these are the two maximal parabolics inside of G2. And one more thing to note is that G2 is self-dual. So it's its own dual group, and passing to the dual switches the roles of the long and short symbol roots. So if you take beta check, this is you can beta check comma alpha check is a pair of a long and short symbol root for G2 check. If that makes sense. Okay, and now I think I get to the three main steps. Yes, okay. So here they are. This first step is to find, the first step is to induce up to G2 from GL2 via the long root parabolic and find the resulting automorphic representation that you get in cohomology. So for this step, I'm going to be very general, and I'm going to assume just that the weight is at least 4, but n is arbitrary, and f is even allowed to be Cm here. So a lot of the assumptions that I need in the final theorem don't actually need to be in play in this section. But I will assume that the L function, the symmetric cube L function of f vanishes at the central value.
And you still need trivial Nabentypus?
Oh, yeah, I forgot to put that in. That's right. Yeah, you still want trivial Nabentypus. Thank you. Yeah, you're absolutely right.
Were you assuming the root number was -1? Why is that?
I'm not assuming. So on the previous slide, I had the root number was always -1 when the level is 1. So that was a remark.
So this assumption about the vanishing, if the root number is 1, is a very serious assumption.
Yes. So for I guess you can do this entire step when the root number is 1 as well. It's just that the next step won't work if the root number is 1. So we'll get to that when we get there. But yeah. But yeah, the root number will be important in the future. But for now, we can just assume that the L function vanishes, and that's enough. Okay, so I'm going to induce parabolically our automorphic representation of GL2 pi f along this long root parabolic p to something that I'm going to call big pi. So this big pi is an automorphic representation of G2. And more precisely, the way I'm inducing it is big pi is the Langlands quotient of this induction. So this is an induction along the long root parabolic to G2. Pi f times this power, this particular power of the modulus character for p. So this 1/2 is just there for normalization's sake to make things unitary, I guess, or to take a unitary induction. So you could say this is the unitary induction of this tensor with delta p to the 1/10 if you want. And this 1/10 here is a normalization factor that sort of shifts things to have central value at 0 if you want. This 1/10 will show up if you write down the L functions that appear in the constant terms of the Eisenstein series coming from this induction via the Langlands-Shahidi method. This 1/10 is because in those L functions you'll have an L function of 5s, and that 5 will cancel with the 1/10 to give you a 1/2, and that's the central value. So what we want to do is we want to locate this representation of G2 of the finite Adels, which I'm calling big pi sub f, the cohomology of the locally symmetric spaces attached to G2. With this particular weight, which I'll say what it is in a second. But so before I do that, let me just say is H star of xG2. So this notation is meant to be a compact way of writing down a certain direct limit of a bunch of either group cohomology groups, or if you want, also local systems on locally symmetric spaces attached to G2. And here, this lambda naught is a highest weight of a certain representation, and that lambda naught is given by this particular weight, whatever it is. And V lambda naught denotes the representation of G2 of that highest weight. So what we want to do, just to summarize, is we want to locate exactly where the finite part of this Langlands quotient appears in this cohomology space. And it's in the cohomology space it's going to appear in is the one attached to this lambda naught.
So if you had
because-
weight 4, this would be the trivial representation?
Yeah, if you had weight 4, this would be the trivial representation. That's right.
Okay.
Yeah, it will appear in just the cohomology of the locally symmetric spaces in that case. Various degrees. Yeah, weight 4 does work. It's weight 2 that gets a little tricky because then you have to start thinking about like limits of discrete series and things like this. Okay, but in any case, so right, so we're going to try to locate this Langlands quotient in this representation of G2 of the finite Ls, which is this direct limit of cohomology spaces. I didn't write a direct limit, but this is what the notation is meant to represent. Okay, and to do that, I'll just say a little bit about it. So we want to locate pi f separately in both the following cohomology spaces. So the cohomology that I wrote on the previous slide is going to decompose into both Eisenstein cohomology and Cuspidal cohomology. Eisenstein cohomology you can think of by work of Franke and Schwarmer. You can think of Eisenstein cohomology as just the GK cohomology attached to certain spaces of automorphic forms coming from Eisenstein series. And the Langlands-Shahidi method that I keep mentioning is going to tell you that these particular spaces of automorphic forms, because I'm assuming that a certain L value vanishes, these spaces of automorphic forms are going to have a nice structure by the work of Franke and Schwarmer. So the Langlands-Shahidi method will essentially tell you that certain Eisenstein series will not have poles because of the vanishing of the L function. And that fact is going to contribute to this work of Franke, or contribute via this work of Franke-Schwarmer to the fact that these spaces of Eisenstein series have a nice structure that you can compute their cohomology explicitly. So that is something, I guess that's even available. I put that on the archive last year sometime. And along with this step as well. So you have to locate it both in Eisenstein cohomology and its complement, which is Cuspidal cohomology. And here is where you need to assume Arthur's conjectures. So here you need to classify the cap forms, so the Cus forms that look everywhere like this Eisenstein series or this Langlands quotient. You have to classify exactly which ones occur in the discrete spectrum, and you have to know what they look like at infinity, because when you take the GK cohomology, you need to be able to compute that. So you need to
get back to my question. So Arthur in the classical groups gives you a recipe. Are you saying that Gahn and Gurevich show that recipe applies, or conjecture the same recipe for G2 or all exceptional
exactly,
groups?
yes. Yeah.
So the
Exactly.
recipe is you look at SL2s and you look at images of SL2 in the dual group, in the product, and up to conjugacy. That's the recipe you're talking about.
Exactly, yeah.
It's his description of the discrete spectrum. Okay.
Exactly, yeah. You will need to manipulate some Arthur parameters and so on. Yeah.
And this is believed to be true for all exceptional groups without modification?
Well, I mean, it's not going to give you exactly the same formulas, but there is a multiplicity formula that was conjectured by Arthur when he originally made these conjectures, and that particular formula is very general, and it is believed to hold, as far as I can tell, for all groups. But
yeah, at some point he was just describing the non-tempered stuff in terms of unipotent and things like that. But of course, in his recent work, he gives the exact description of a discrete spectrum.
Right.
And
so
I'm very I'm amazed. I mean, I know that for G2 and for some other groups, maybe people have established some parts of it. But I think Arthur was nervous about making such a exact statement in general. Anyway.
I see. Well, in any case, Gad and Gurevich have partial results towards the pi f isotypic part of this conjecture.
Okay. Mm-hmm.
Yeah. And I think it's very reasonable for it to be believed to be true. It's a statement about cap forms, essentially.
Yeah.
Analogous to P-adic Shapiro's work.
Right. He also described them. Yeah. Mm-hmm. for,
Yeah.
especially for groups like G2. But I think if you go to E8 or something, I think I'd be a bit nervous.
Yeah, I would be a little bit nervous too. Yeah, but G2 is pretty small and pretty workable. Okay, so right, so what I guess what we're saying here is that you have to assume some version of Arthur's global multiplicity formula to locate exactly what part of the, I guess, what part of the discrete spectrum will contain representations that look locally like our pi f, and then the fact that you don't have any residual Eisenstein series because you don't have poles for these Eisenstein series coming from, again, the Lagrange method tells you that these are actually going to be in L2 cusp. And then you have to classify what they look like at infinity when you take their GK cohomology. And that's something that I do. I use Adams and Johnson's work to explicitly describe the local Archimedean Arthur packets for these particular Arthur parameters that you get for that need to be studied in order to make this precise. Okay. And then one thing to note is that in cuspidal cohomology, this automorphic representation, or its finite part, appears in different degrees depending on this sign, which is, I guess, what you were asking before as well. So this sign, if it's, so it goes like this. If this sign is -1, then the Archimedean Arthur packet tells you, or the global multiplicity formula tells you that the element from the Archimedean Arthur packet is discrete series that is contributing to cohomology. So it appears in middle degree 4. 4 is middle degree. And otherwise, it's non-tempered, and it's a Langlands quotient of a parabolic induction itself. It's actually pi infinity. It's actually isomorphic to pi infinity in that case. In that case, it appears 1 away from middle degree in degrees 3 and 5. But we won't really need to care about the that case in the end, because we're eventually going to assume that our level is 1, and then we'll have that the sign is -1, and then we'll get a discrete series representation. Okay. So one thing I should say now in the second step, so the second step, so one thing I didn't really motivate so far is exactly why we need to find every single instance in cohomology. Like, why isn't one instance of pi f in cohomology enough? And it has to do, the answer has to do with the way we're p-adically deforming this big pi sub f, this finite part of big pi. So now we'll do the p-adic deformation, and I'm going to assume that p does not divide n, the level. So we can do a lot of the p-adic deformation step for general n, but then in the end, we will have to restrict to n equals 1, as you can see sort of hidden down here. But we'll get to that. So what I need to do is I need to take a particular critical p stabilization, which I'm going to call sigma of pi. And this p stabilization, so p stabilization in the sense, when you're talking about p stabilizations of modular forms, it means you're picking a root of the Hecke polynomial, and you're picking a UP eigenvector for an eigenvector for the action of UP. So the analogous thing is happening here. You can take a p stabilization; it will be critical in that case. So it's like a slope k-1 form in the GL2 case, in a sense. And this p stabilization will depend in part on a p stabilization of f itself, so the GL2 thing. This is a p stabilization of a form on G2, and that will depend on a p stabilization chosen for the form on GL2. And hence on a root, which I'm going to call alpha p from now on, of the Hecke polynomial for f at p. So I'm going to take a critical p stabilization. I can describe why I need critical in a moment. I mean, they're all actually going to be critical, I think, but I need to take a particular one, which is critical. And I'm going to use the data obtained in step 1, along with the machinery of Urban's eigenvariety, to compute a certain multiplicity. So this multiplicity is why I needed to locate every single instance of pi f in cohomology. So I'm going to compute something called the cuspidal over convergent multiplicity of this p stabilization. And the cuspidal over convergent multiplicity can be expressed in terms of certain other multiplicities, one of them being the multiplicity with which pi sub f appears in cohomology in the usual classical sense as in step one. So when you compute this multiplicity, you'll get a sum of a bunch of terms, and one of them is the classical multiplicity that we computed in step one by locating every single instance of pi in cohomology. So this will be some alternating sum over degrees of cohomology, and so you need to know exactly which degrees they're appearing in, and so on, and why you get every single instance of pi f as well. And so once you've done that, when the level is 1, things are somehow nice enough in a way I'm not going to be too precise about in this talk, but things are nice enough so that Urban's eigenvariety actually p-adically deforms this sigma of pi, this critical p stabilization, in a generically cuspidal family, which I'm going to call script E, over all p-adic weights for G2. Okay, and one more remark to make is something I had said before, but when n equals 1, we always have the sign of the functional equation is -1. And this is one reason we assume n is 1 is that the cuspidal over convergent multiplicity I expect to be 0 when n is, or when epsilon is +1. But when epsilon is -1, I can show, at least under the assumptions that I had in step 1, that it's always at least 3, and I expect it actually to be exactly 3.
And this sign -1, is it true for odd symmetric powers, period? What's special about sim 3?
Well, I know, so the way I compute this is I look at the triple product. So maybe it is also the same, but you're in the balanced region for the triple product if the sign is, if n is 1. And then that for level 1 forms, the triple product has sign -1. But yeah, I actually don't know if it's always, it probably is, but I don't know a proof off the top of my head why it would be the case for, like, when what I'm saying is that when the conductor is 1, I think probably the sign is of odd symmetric powers is always -1, but I'm not sure. I don't know a proof off the top of my head. I would expect that to be true, but I'm not 100% sure. But yeah, the sign is -1 in this case. And so that shows by the previous step that somehow that things are contributing to cohomology in the right way to see a non-trivial cuspidal over convergent multiplicity. That's the very rough sketch of this argument, on the automorphic side at least. Okay, and then the last thing to do would be to go over to the Galois side. So here's where I'm assuming this global Langlands conjecture. So now we assume n is 1 so that we do get a p-adic deformation in general to a cuspidal family. We're also going to assume here that f is not Cm. So I think now I have all the assumptions in place that we had before. Since f is not Cm, this Galois representation rho f has large image in a certain sense. And so one consequence of that is that not only will sim cube be irreducible, so will sim squared be. Okay. And so assuming this global Langlands correspondence, which I'm not going to state very precisely here, but I will say part of the global Langlands correspondence we need to assume does come with some p-adic Hodge theoretic data at P. So we do need to know that if you're unramified at P, then you're crystalline. I mean, yeah, if the form is unramified at P, then the Galois representation is crystalline with certain slopes for Benius. But assuming this, what I do is I construct a Galois representation of GQ into the dual of G2, which is, as I said before, it's just G2. And it's valued in the ring of analytic functions on E. But okay, so to make this really precise, I have to really take like the fraction field and then algebraically close it to actually get a Galois representation. And in this Galois representation, in some sense, interpolates the other Galois representations for the members of this p-adic deformation E. So E, remember, was a p-adic deformation of pi, big pi, over weight space, and the Galois representation here that I'm getting here is interpolating the Galois representations, which I'm assuming exist for the other members of E, or at least the classical members of E, with sufficiently dominant weight. And the key input here is to use Laforgue's pseudo characters. So you want something like a pseudo representation for a reductive group in order to get this to land in G2. And that has been developed by Laforgue. Okay, so then we have to construct a particular lattice L inside of this Galois representation that I'm calling rho E, and use a rivet style argument to show that when you specialize this lattice, if you've chosen it correctly, back to our Eisenstein point, then you get an unramified everywhere away from P and crystalline at P extension like this. So this is an extension E of QP bar by the correct twist of sim cube. And so the class of this extension is exactly the non-trivial element in the block-Kato-Selmer group that we were after. This is the rough idea of, or the rough overview of the entire argument. So I have a picture of this actually. This is what I've been calling the Skinner-Urban method, because Skinner and Urban were sort of the first to do it in this kind of setting. They did it for modular forms instead of some cube of modular forms. They also did it for unitary groups as well. But okay, so here's the picture. You start with a pi, which is my pi f in this case. And this is somewhat more general than just the situation I've put myself in with G2, but you start with pi on some Levy subgroup of a parabolic subgroup inside of some reductive group. You lift it to a big pi, which is some parabolic induction in some way of little pi. And you deform that in a p-adic family E, and you transfer over to the Galois side from there. Then you'll have this rho E on the dual group. Its Galois representations should go into the dual group. And then you construct this lattice L and reduce mod some maximal ideal of some local ring, or in other words, you specialize to the Eisenstein point. And you get some rho L bar. And then if you did everything right, this will not be the Galois representation attached to pi, but it will be, so it won't land in M, but it will land in P instead, or P check rather. So it won't land in M check, it will land in P check, this rho L bar. And the failure of this diagram to commute will be exactly measured by some cocycle in a block-Kato-Selmer group. So that's the rough idea of the whole argument. It's basically Ribet's method, but for block-Kato-Selmer groups instead of class groups. Okay.
So what you're using about G2 is that N is sim cubed as a representation of M. Is that what you're using?
Almost. N is gonna, so on the dual side, yeah, you have a sim cube appearing in the N check here. You also have a determinant as well.
Okay.
And that determinant is actually important. It's sort of part of the numerology of this whole thing.
But
yes,
if you're willing to assume sort of global Langlands and Arthur for like any particular group, you would get like a theorem for any group. Just
as long as N check had the right shape, I think you could try to start building an argument, but it's a very non-trivial process to actually build that argument correctly. But yeah, you can imagine doing this Skinner-Urban method for any G and P for which N check for P check had the right shape. So you want not only the representation you're after to appear in N check, but you also want some determinant or something one-dimensional in some sense.
And is your calculation not very closely, as you said before, related to the Langland's Shahidi method and the symmetric cube being in G2? That's how they meromorphically continue the symmetric cube as a constant term. I mean, this goes back to Langland's this example.
Yes, exactly. Yeah. So that is exactly what you're seeing on the automorphic side in order to get enough nice information about this big pi at infinity to p-adically deform it.
But I guess Tony's question was, you suppose if you're putting in the full Langlands conjectures, then you should be able to relieve yourself of this kind of, I mean, the Langland-Shahidi method is very restricted.
Yeah, that's right. Yeah, but this is somehow even more restricted actually, because n check needs to have a particular shape as a representation of m check.
All right.
Yeah.
Sorry, this is maybe more on the same line of question, but so you mentioned that you had to compute Eisenstein cohomology, but what role does that play in this argument? I would have thought you're just using the cap form.
So you have to know the role that it's playing is when you're computing this multiplicity that I described in step 2. So you need to, it's somehow like an alternating sum over all degrees of cohomology of all instances of your form inside of cohomology. So you need to know everywhere where it appears, not just in cuspidal cohomology, but also in Eisenstein cohomology. This is somehow, you know, when you look at Urban's eigenvarieties paper, he has all these multiplicities everywhere, and this is what they are. They're looking at all instances of things in cohomology.
I see.
Yeah.
Okay, thank you.
Cool. So if there are no more questions, let me move on to describe a little bit this last step, this step 3, in a little bit more detail. Okay. So more on the lattice L in this case. So I'm going to take R7 to be the 7-dimensional representation of G2. It has highest weight alpha plus 2 beta here, which was some dominant root for G2. And this is the picture of all of its weights. So as a representation of M check, which was the short root parabolic, this G, which is GL2, we have the following picture of well, we have the following picture of M check acting on P check via the adjoint action. So we have like 3 blocks. We have 3 different blocks. One of them is the standard representation of GL2. The last one is the dual of that. In the middle is the adjoint representation, the 3-dimensional adjoint representation of G2. You can sort of see that from the weight diagram I drew in the previous slide, because up here you see the standard representation. So beta is the short root, and beta is this one right here moving in this direction. So when you act on this lattice of weights by the adjoint action, you're going to see root strings in the direction of beta. And so the top one is going to be the standard representation. The middle one is going to be this adjoint, and the bottom one is going to be the standard dual. And then the unipottent radical will be like entries up above these 3 blocks. And so this shape is going to be very important when we're actually studying the lattice. Keep this in mind if you can. So I'm not going to go over the construction of the big representation, like the family of Galois representations, rho E. I'm just going to assume we have it, but I will go into some detail on how you construct the lattice inside of it. So just assume you have some family like this, specializes at classical weights to Galois representations attached to automorphic forms on G2. And in particular, since everything was level 1, you know, these automorphic forms will be crystalline at P, and this is something we also needed as well, and unramified everywhere else. So this whole representation somehow is unramified at everything but P, and at various specializations, it will be crystalline at P as well. Okay, so at the Eisenstein point, this rho E specializes to the Galois representation attached to this parabolic induction pi. And so that is just, you know, so you start with the Galois representation attached to the particular twist of little pi f that we took before, which is going to be this guy. Then you include it as the levy of P check into G2. So you compose this inclusion with this Galois representation. And so the picture you get is very similar to the thing we had just seen. You get, the standard representation of this Galois representation up here. You get its dual down here, which I'm just writing as the same thing, but with a different twist. And in the middle, you get the adjoint of it. So three-dimensional representation in the middle. So R7 composed with rho pi looks like this as a block diagonal Galois representation. And so here's how you would construct L. So you want to choose a lattice L inside of, so you have to, in order to even make sense of a lattice, you somehow need to force it through this representation R7 or some other representation if you want. But R7 is the simplest, so I went with that. I don't know if you can actually do it with like the adjoint representation or something, but anyway, so you need to choose a lattice L inside of something which is factoring through GL7 here in this case, whose specialization L bar at the Eisenstein point has irreducible quotient, this bottom thing from before, this guy. So you want this to be the irreducible quotient of whatever specialization of the lattice you're choosing. So there are three cases. Either this whole family of Galois representations that I called rho E before, or equivalently, I guess any lattice inside of it is generically irreducible, in which case you get Galois representation with this shape, or if it's generically irreducible, but somehow the blocks end up in the wrong order, then you get a Galois representation with this shape. So here, the difference between the first two blocks is just the order of the block diagonal terms. So yeah, one thing to note is that if the whole family of Galois representations is generically irreducible, then this star 1 and this star 2 are going to be non-trivial. They're not going to be 0 because everything has to be generated by some vector inside of this row F at the bottom here. And then finally, if it was reducible, then after some work, you can show that actually it has to take this shape. So here you get if it's reducible, one can show that there are two sort of up to semi-simplification. There are two representations in it, and then when you specialize, one of them becomes this extension, and the other one becomes this adjoint. So let me just say you can rule out other reducible cases using just some observations of p-adic theory. You can look at what the slopes of everything of the crystalline Frobenii are on the blocks, and you'll have to see that somehow you'll get a contradiction with Newton and Hodge being in bad positions. But in any case, if we rule out these last two cases, ear 2 in red, as I called them, then we'll have that our lattice specialized at our Eisenstein point looks like this. And this is good because this looks a lot like the picture of P check I showed you before. And we're actually going to need to use that in the end. We're going to want this Galois representation, or the specialization, this specialized lattice, the specialization of this lattice to factor through G2. And it will even factor through P check, as we expect from the picture I had drawn before of the Skinner-Urban method. And so to do this, we'll make use of the fact that rho E itself factors through G2 to put restrictions on the specialization L bar. So what does it mean for rho E to factor through G2? What does that buy us? So, well, here's a fact. The fact is that G2 is the stabilizer inside of GL7 of a generic alternating three form. So there's a definition of generic for an alternating three form. It just means that when you translate it by GL7, when you act on it in the natural way by GL7 in the space of all alternating three forms, you get a Zariski open subset. That's all that means. And G2 is the stabilizer of any such three form. G2 will appear in different ways inside of GL7 as a subgroup, but every instance is the such a stabilizer like this. And we'll get a generic alternating 3 form, which I'm calling, brackets with a tilde on the big Galois representation, family of Galois representations, rho E. So this will have rho E, but we'll preserve this some 3 form on, I guess, frac of OE to the 7th, that vector space. And then after rescaling, we can reduce it mod the point corresponding to the lattice, the Eisenstein series that we're the Eisenstein point. So after rescaling, we could specialize the Eisenstein point, and it reduces to a non-trivial alternating form, which I'm going to call the same thing without a tilde, which is preserved by the Galois action on L bar. Okay, so all we know now is that it's non-trivial and alternating. It's a non-trivial alternating 3 form. We don't know that it's generic yet, and that's actually kind of a difficulty. So I'll take you through how this argument sort of works from here to try to show not only that these 2 cases can be ruled out, but that the form that we actually get on the specialization L bar is generic. So now we're assuming, for sake of contradiction, that one of these bad cases holds. So we're either in, the blocks are in the wrong position, or star 1 is trivial, this kind of thing. But in either case, you see that you get as a quotient something that looks like this extension here. So I guess I'm really thinking about this one because I called it star 2 here, but okay. So you get as a quotient something, an extension of this form of rho of F twisted by minus k over 2. So remember k was the weight. By the same thing, but twisted up by 1. Okay, so here's the picture again. So what I do is I study this form very explicitly in some sense, like, I make all sorts of computations with it, like of generic matrix coefficients, so on. You can compute matrix coefficients of matrices, specific matrices of these forms, using the fact that those matrices preserve this alternating form. And actually, one can show that it's sufficiently non-trivial to force there to be a sub-representation of this form inside of the exterior square of this extension. So the exterior square of this extension, E prime, as I'm calling it, will be some 6 by 6 thing, and it will have a block in it that looks like this. But that block might have some things below it as well in the matrix representation of it. But the non-triviality of this form is actually enough to force the block below it to be trivial. So we actually get this as a sub-representation of the exterior square, in a very short sort of summary. That's how this works. So if we can get that this E double prime, as I'm calling it here, is crystalline, then what happens is that we get this E double prime is a class in the Selmer group of QP twisted by 1. So, which is a trivial group by, because the units of Z are plus or minus 1, if you want, by computations of Bloch and Kato. This will be a trivial group, and that will be a contradiction, ruling out the first 2 or the second 2 cases of the shape of the lattice. So this red 2 and this red and this year 2 that we had before. So that will be the contradiction that we're seeking, if we can show that this guy right here is crystalline. So it's naturally unramified at all places besides P, because the whole Galois representation that it's coming from is unramified at every place besides P. But crystallinity is a little more subtle, maybe much more subtle, because the one thing you'd want to do is, as Skinner and Urban do in their work, is they use this lemma of Kissen. So this Kissen lemma that interpolates crystalline periods from other members of this family E to a particular one for the specialization of this lattice. But what happens is kind of interesting here. when Skinner or Bond do this for GSP4, for instance, to tackle just the case of modular forms instead of their symmetric cubes, Kissin's lemma is just enough to get something to be in this Bloch-Kato-Siller group I displayed before, this Bloch-Kato-Siller group. But in this case, we actually get the wrong period. So in other words, the period that we get that what we end up getting is that some Galois representation has some non-trivial decris, but the Frobenius eigenvalue of those things in decris are the wrong Frobenius eigenvalues. We want them to have Frobenius eigenvalue 1 because that will correspond to, go back here, that will correspond to a Frobenius eigenvalue for this guy right here, this quotient, which is what we want. But we get the wrong period. We get a period with a much lower slope crystalline Frobenius eigenvalue. But we can actually make do with that using the following interesting, I thought it was interesting, at least, proposition, which says that any extension, I'm going to call it E naught, of rho f by rho f of 1 is semi-stable. And the possible filtered phi n modules that you can get from these extensions can be even described explicitly. You can make quite explicit exactly what modules can appear as the DST of these guys. So how do we use this? So we get any extension like this is semi-stable. And so how do we use this? This proposition in combination with a non-trivial crystalline period can be used to describe exactly what in the exterior square of E prime. So remember E prime, let me go back just to be clear. Wow. Okay, click a little slower than that. So E prime is this. So E prime is like an extension in this proposition, but twisted down by minus k over 2, but that's okay. Maybe, yeah, okay, great. So in the exterior square, you can describe explicitly the n on the exterior square here. And you get that the phi equals 1 part of DST, when you just look at everything explicitly, actually lies inside the kernel of this n. So you apply Kissin's lemma, actually you apply Kissin's lemma to the exterior, I guess you apply Kissin's lemma to E and its dual. And you put that information together to describe the n for the exterior square. So this is going to be a crystalline, this is going to contain only crystalline periods, this part of DST. So DST of this extension, E double prime, is actually an decris of the exterior square. And so E prime, double prime, which was our extension of QP by QP of 1, is crystalline as desired. So that rules out, ultimately, what that does is it rules out those two bad cases of the shape of L bar and shows us that L bar has this correct shape that we wanted. So then from here, we're pretty close. So maybe I should ask if there are questions about this method or anything like this before I go on. If you have questions about this, please speak up. Be happy to take them. Okay, so from here, we're pretty close. So we get L bar has this shape. Like I said, we wanted L bar to factor through G2. So first of all, this star 3 right here, this extension of add by rho f of 1 minus k over 2, gives us a class in the tensor of rho f twisted by 1 minus k over 2 by the dual of add, which is just add again, of rho f. And then this representation is some 6-dimensional representation, and it splits into these two components. So it splits into rho f dual, twisted by k over 2, and the symmetric cube, the twist of the symmetric cube, or the dual of the symmetric cube that we're interested in. And so then one can show from here, one gets enough information by knowing that the blocks have the right order to show that this alternating form is actually generic. So this L bar actually does factor through G2 and further through P check. Just because P check is all the matrices inside of GL7 that are in that block form. And this has two consequences. The first is that star 3 is non-trivial, And this is because star 1 is. So actually, I did it again. Let me go back here. Yeah, great. So star 1 is this guy and star 3 is this guy, but there's some duality between them because of the fact that this factors through p check or G2, either way. There's some duality between star 3 and star 1, and one is non-trivial if and only if the other one is. So this shows that star 3 is non-trivial because star 1 was. And the contribution, furthermore, the contribution of star 3 to this piece is trivial. To this piece that with just the row F, that's trivial by well, some matrix coefficients computations you can do on the thing. You know, we would expect that that this class would factor through the sim cube because that's what appears in the unipotent radical of p check, and indeed it does. We can just do a computation and show. So we get a non-trivial class inside of the correct cohomology group, and we just need to show it's crystalline to show it's in the Selmer group. So let me just very briefly describe in the last 4 minutes how that works. So for crystallinity, we need to use this Kissin's lemma again to interpolate crystalline periods from the other members of E to the members of L bar, or just to L bar. But then again, this actually gives the wrong period. So again, we get a period that has the wrong Frobenius eigenvalue. But there are other like very different tricks from p-adic Hodge theory that I don't have time to explain here, but one can use them to again show that we can make do with the period that's provided by Kissin's lemma in this case. So one interesting thing just to say, because I think it's interesting, one thing that this involves is a possible switch of the p stabilization. So if you switch this p stabilization of F, you switch the p stabilization of sigma pi. When you do that, you get a whole different family. But there's an argument where you switch the whole family. If one family doesn't work, then the other one does. There's an argument one can make in this direction, but I don't have time to explain it here. The whole thing. The only thing I can say is the end result, which is that the star 3 actually provides you a non-trivial element in the correct Bloch-Kato-Silver group. So it is crystalline. One can make sure that it is crystalline, depending on this choice of alpha p. All right, and I guess I can finish even 3 minutes early, so thank you for listening. Yeah. So I can take questions.
Okay, let us first unmute ourselves and thank Sam for his wonderful talk.
Thank you.
Questions?
Well, any other questions? Anybody want to know what this is? This is a drawing of G2. It's a two-dimensional torus with 12 unipotent directions coming out.
So,
by the way.
Sam,
Yes.
my first approach to this would be to think of something like symmetric cube as automorphic. That gives me something self-dual on GL4 here. Transfer to a unitary group, run it through my work with Eric. But the problem there is you only get something in a cohomology class over an imaginary quadratic field.
Right.
I don't know how to separate it. So here you're really getting something over Q. Is that correct?
That's right. That's right.
Yeah. So you're avoiding this problem with the imaginary quadratic fields. Okay. Good.
Yep. Another thing that one could try is to move it to GSP4, but then the numerology, of course, doesn't work out. The numerology involving, GSP4 inside of say GSP6 doesn't quite work out.
Since your method seems, I think, closely connected to Langland-Shahidi, there are other symmetric powers that.
Yeah. So I actually don't know which ones appear. Do you know by any chance?
Well, there's a list in Langland's book on Euler products.
Right, I guess in the appendix to Euler products you can find it.
Yeah, he's got a complete list there of all L functions that you can get through Eisenstein series through such devices. But you can certainly get a fourth symmetric power, since I used it once with Kim.
Yeah, but that will not be amenable to this sort of on the Galois side, because the even symmetric powers are problematic because of their central value being, not being integral.
Mhm.
So now you don't expect to get the same kind of results on the Galois side for even symmetric powers.
Actually, Chris, can you explain what's the problem with being over measuring quadratic field? You said.
Oh, it's just, I mean, there's no problem. I mean, you could probably do it via the method Skinner just described, but you'll have a K here instead of a Q. That makes sense? Or K is an imaginary quadratic field. So you'll get a slightly weaker result.
So in the Skinner-Urban method, you end up with like an interpolated statement, like an Iwasawa main conjecture statement. So do you sort of pass through an Iwasawa main conjecture analog?
So the Skinner-Urban I'm talking about is not the main conjecture Skinner-Urban, but the block cutoff Skinner-Urban. So no, I don't. Yeah.
Okay, thanks.
Yeah, no worries. I feel like the first question I got was not, or maybe the second was not completely answered satisfactorily. Maybe if you could come back, or maybe it was. I don't know. Maybe. Not sure. Cool.
So you had some earlier question about the overconvergent multiplicity and the reason you had to compute that, and that's because you're working with, because the G2 somehow, I mean, with unitary groups and things like this, we could use holomorphic objects, and we didn't really care about multiplicity. So
exactly.
As long as
yeah. So this is a very good point, that G2 does not have a Shimura variety. So p-adic deformations on G2 really have to go through Eric's paper.
And if you try to do this just with like GL, what goes wrong?
GL what?
GL, I mean, take a Eisenstein series for GL5 induced from GL4 or something like this.
Well, then you don't even have discrete series.
You still have cohomology. So
yeah, but I don't know how to p-adically deform that without having discrete series and using Eric's paper, for instance.
Right.
Yeah, when Eric sort of pitched this idea to me, the way he did it was after Aaron Pollock gave a talk here, Eric just looked at me and said, G2 has discrete series. And sort of that was the beginning of it. But I guess that was sort of a main point for him, was that you can't hope to p-adically deform, at least not with the tools we have right now, unless you have discrete series. Cool. Can I thank you guys for being a very interactive audience? I really love getting lots of questions during the talk. That was great. Yeah. I'll thank you guys instead of you thanking me.
No, thank you, Sam.
So I'm glad you view it that way and not that we pests, because that's, I try to get people to do that, but in my class, nobody ever says a word. So I don't know.
Yeah.
Zoom is
sometimes I give a talk and nobody says anything too. Yeah. So I'm glad people are interacting. Yeah.
Okay, let me end the recording. If you want to be here and have some chat, you can feel free to do so.